get started. Dear Heavenly Father, we thank you for this opportunity we have to, whoa, was that me? Oh, that's okay. Meet together and study your creation. Thank you for cell phones. Also, keep us in touch. And I just pray that you'd just bless this class, help us to understand what we go over, and you encourage the students if they're feeling discouraged after the test. I know I might be. Amen. I mean, the odds that any of you finished that test well, they're not good. But maybe some of you surprised me. We'll see. So today, talk to you about systems of differential equations. Now, in fact, these are systems of ODEs, really. In other words, we're still dealing with a case where we just have one independent variable, but now we might have more than one dependent variable. All right. So we'll get to that. But before we even get to that, we have to go back and pay our dues, so to speak, and just talk about the preliminary topic, which we should deal with, because depending on your high school experience, it may be more or less developed in your mind already. But the preliminary topic is systems of linear equations. So we'll learn that systems of linear equations, the way to solve those, the way to understand them, really, the best way is with matrices. And so if we develop this idea of a matrix, a box of numbers that encodes a linear system, it allows us to solve linear systems in a nice way. And those same matrices are useful for us as we solve systems of differential equations. All right? So let's just talk about a system of linear equations. So an example, something like this. 3x plus 2y equals to 7, and x minus 2y equals to 8, right? Does this system of linear equations, this is two linear equations and two unknowns, all right? Hopefully you solved these in high school. Can you tell me, does this have a solution? You should be able to tell me whether or not this has a solution just from looking at it without further calculation. Why? Geometrically, what is this? These are lines, right? So this is just a funny way of writing the equation of a line. And you should be able to look at the equation and tell if the lines have the same slope or not. It's fairly obvious that these lines do not have the same slope, right? You could solve for y equals mx plus b if you like, but I can just kind of eyeball and say, oh, not same slope, which means that the lines have to cross somewhere, right? That somewhere they cross is the solution. Now, I don't recommend you solve it graphically. The way I'd solve it is to add equations, personally. So this would be 4x, the two y's cancel, you get 15. X is equal to, what we got? 15 over 4. And what's that? Then y. Pick your poison. I need to just take one of the equations and solve for y, right? How about I'll take the first one. Y is equal to 7 minus 3x over 3, right? Oh, 2. I can't do math. All right. It's okay. Don't tell anybody. And whatever that is, I don't really care. That's not really the point of what I'm doing here, but I'll finish it just for the sake of finishing it. 15 over 4. What do we got? Excuse me. 7 minus 45 over 4 divided by 2, which is what? 28 minus 45 over 8. And whatever that is, I don't know. Minus 17 over 8, right? Okay. So this method I just used is a combination of what I would say adding equations and substitution, right? Let me show you how to do, actually let me not, let's just stop there with this example. Example 2 could be something like this. X plus 2y equals to 3, 2x plus 4y equals to 6. How many solutions here? By the way, so before I forget, the first problem, what's the answer? I mean, what is a solution to a system of two equations and two unknowns? I mean, you got choices, right? You can say x equals to 15 over 4 and y equals to minus 17 over 8. So that's like one way you could write the solution, basically in terms of both things. Or, aka, you can write it as a pair, which is 15 fourths, comma, minus 17 eighths, right? This would be another way you could write the solution as that pair. In some sense, the pair notation is better because it emphasizes that x and y don't exist in isolation, that you're solving both simultaneously, right? Okay, now this one, what's the solution? Or I should say, in this case, solution set. It's what? They're parallel, right? And is this... So I guess if they're parallel, you got two choices, right? It's either like this, right? Or it's like this. I mean, they could be the same line. In this case, it is actually the same line, right? Because I just took this to get the second equation and multiplied the first one by 2. What's the solution set then? All points. That's kind of true, but all x would be fine. But how about this? It's x comma y such that what? We could say x is equal to 3 minus 2y, and y is a real number. One way you could write it, right? So another way to express that would be, say, 3 minus 2y, comma y, such that y is a real number. I kind of like the second one I wrote, I like more. I don't know. They're logically equivalent. In other words, every point on the graph of the line is a solution. Because the equation, I mean, those lines intersect itself everywhere. Now, if we didn't have the same y-intercept, then we would have no solutions at all. All right? Now, the reason I'm going over this example is you're like, I don't really need you to do this. I already know how to do these. That's probably true. But it's important conceptually to notice the difference here, right? We have two different kinds of systems. We have a system with a unique solution. We have a system with infinitely many solutions, right? In fact, and if you allow for the black, I mean, so this one's like the black. The red here, how would I get the red system? Let me make that be example 3. Example 3, what if we had like x plus 2y equals to 4 and 2x plus 4y equals to 6? Then we'd have the situation that they don't have the same y-intercept, right? They'd have the same slope. They wouldn't have the same y-intercept. And so graphically, you can see that the solution is something like this. There's no point of intersection. Those are heuristic. I don't really know if it has a positive or negative slope. I haven't worked it out, okay? We could figure it out pretty fast, but that's not the point. The point is no solutions for example 3, right? Okay, so there's apparently 3 cases. A unique solution, infinitely many solutions, right? Or no solution at all. You're like, well, that's just the second order case. What if we had 3 equations and 3 unknowns, or 4 equations and 4 unknowns, or 5 equations and 7 unknowns, or other flavor varieties of systems of equations, right? It turns out, if you're working over the real numbers or the complex numbers, it's still the case. These are the 3 things that happen. You either have a unique solution, you have infinitely many, or you have none at all. That's it. There's never something like the quadratic equation where you solve a linear system and you get two solutions, right? Or you can have quartic equations where you just get 4 solutions. Like that cannot happen for linear systems if we're working over the real or the complex numbers. Now, if you're solving systems of linear equations over like binary numbers, over z mod 2z, over finite fields, then other things are possible. But here, we're just thinking about complex and real numbers. Okay, so here's the definition for you. If we have something like this, a1, 1, x1 plus a12 x2 dot 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 plus a1n xn a21 x1 plus a22 x2 plus a2n xn, all right, and so on down the line. Eventually we get to am1 x1, am2 x2 plus amn xn. But at the moment, these are just linear combinations, all right? I haven't made them into honest-to-goodness equations yet, right? So here, let me say this is equal to b1, this is equal to b2, and so forth on down the line until we get a equals to b. How many equations do I have here? 1, 2, m of them. So b sub m, right? This generically is m equations in n unknowns. What are the n unknowns? In my current lingo, x1, x2, xn, all right? Those are the unknowns. The b sub 1s through b sub m's are usually called the inhomogeneous terms. So like if all of the b's are 0, this is called a homogeneous system of linear equations, right? Otherwise, it's called an inhomogeneous system of linear equations. Okay, so we define something called matrix multiplication. By the way, the a sub ij's, I should mention, a sub ij's are the coefficients of the system. Here we have 1 less than or equal to I less than or equal to m, and 1 less than or equal to j less than or equal to n. So we say that I is the row index, all right, whereas j is the column index for reasons that will become clear in just a second. Row index, column index. All right. So this system of linear equations we can rewrite as what's called a matrix column multiplication, and it's just this. So we have a11, a12, a1n, a21, a22, a2n, and so forth on down the line, am1, am2, amn. So there's the matrix of coefficients. This is it's m by n, m rows, n columns. All right. And then the vector of unknowns, x1, x2, xn. We have n unknowns in this setup here. And then, of course, we have our vector of inhomogeneous terms on the other side. b1, b2, b sub m. So just trying to develop some terminology for you guys, all right? Now, if this was a course in linear algebra, I'd spend a week or two trying to really flesh this out and explain why things work the way they work. But this is not that course, so I'm just going to tell you what happens and just give you the cold, hard truth of what we learn in linear algebra, all right? So we need some language here. Let's denote this thing by capital A, and I'll denote this thing by vector x, and this I'll call just b. Actually, you'll find vector b. So in other words, the system is just AX equals to B if we write it in matrix vector notation. It's pretty neat, right? Now, I told you there are three possibilities when we're solving a system, right? We either get infinitely many solutions, a unique solution, right? Or no solutions at all. Now, you guys know about determinants already, right? I mean, we were playing with them with the Wronskian earlier this semester already, right? So here's one of the theorems. AX equals to B has unique solution. And the unique solution is actually X equals to A inverse times B, where this is not 1 over A. This is the inverse matrix, all right? I gave you a formula for calculating that in the 2 by 2 case. More generally, that's a problem you learn in linear algebra, okay? I'm just saying it's there. There's something called the matrix inverse. You can calculate it. Anyway, it has a unique solution if and only if the determinant of the matrix of coefficients is not equal to 0. All right? Furthermore, if the determinant of A is equal to 0, then either 1, AX equals to B has infinitely many solutions, or 2, AX equals to B has no solutions. So I think you can start to get a sense of why it's called the determinant, right? I mean, it's kind of a, well, I mean, it's kind of punny, but I mean, it determines whether or not there are solutions, right? How do you find the solutions then? Right? I guess before I do that, let's look at an example, example 4. And I'll get back to the big theory here in just a second, but let's look at example 4. So we could have something like x minus 2y plus 3z equals to 8, 2x plus 4y plus, that was supposed to be a z, it turned into a 7. Idiot, that's here, me not you guys, equals 0. Excuse me, let me make that 8 a 0. Excuse me. Great, googly moogly. Sorry about that. 4x plus 8y plus 2z equal to 0. How would you solve this system of 3 equations and 3 unknowns? First of all, if you believe the theorem, we can calculate the determinant of the matrix of coefficients and decide whether we should be looking for an infinite solution set or a unique solution, right? So let's do that right quick. What is the matrix of coefficients here? Right. So you're ordering the variables in the natural way, x, y, z, right? What do you got? We got 2. We got a 4. 1. We got a 4, an 8, and a 2. And that's equal to 0, 0, 0, right? So this is my matrix of coefficients, and this is a homogeneous problem. So what's the determinant of that matrix? I can tell you it's 0 without further calculation, but I know things. I guess what you guys probably would do at the moment is to just calculate the determinant directly, right? Then I'll tell you how I knew. I'll tell you my secret. So that would be 1 times the determinant of 4, 1, 8, 2, plus 2 times the determinant of 2, 1, 4, 2, plus 3 times the determinant of 2, 4, 4, 8, which would be 8 minus 8 plus 2 times 4 minus 4 plus 3 times 16 minus 16. Wow, every one of them is 0. Funny. Now, the reason I knew that was going to be 0 before I even calculated anything, it's pretty simple. It's because row 2 and row 3 are just multiples, right? If I take row 2, I get times 2, I get row 3. So that means the determinant is 0, which means there's either going to be no solution or infinitely many solutions, right?
If it was like row 1 and row 3, would the rules still apply, or is it?
Yeah, if there's any column that's the same, or if there's any row that's the same, or just a scalar multiple of one or the other, the determinant's 0. It's even greedier than that. If I could take row 1 and row 2, add them together and get row 3, determinant's 0. If there's any kind of linear dependence amongst the rows or columns of the matrix in linear algebra, we prove the determinant's 0. So the determinant being non-zero means that all of the columns or all of the rows are genuinely independent. And the determinant's also very kind in the sense that if you switch the rows and columns, if you do what's called transpose the matrix, it's like the transpose of this matrix. I'll show you guys that. So if we take the transpose of this, basically you mirror it over the diagonal. So the first row becomes the first column. The second row becomes the second column. The third row becomes the third column written as a column. So this is the transpose. This will also have determinant 0. The determinant of A is equal to the determinant of A transpose. All right. Anyway, so definitely we're in the purple case of the theorem. Determinant 0, which means we have either no solutions or infinitely many solutions. All right? So another theorem. Well, here's some properties. A times x plus y, guess what that's equal to? It's equal to ax plus ay. Guess what else? If I have a matrix A plus a matrix B, and I multiply by a vector, I get ax plus bx. Let's see here, what else? There's actually a way we can multiply matrices. We'll get to that in a second here. If I have the product of two matrices, actually product of three matrices, matrix multiplication is associative. So here I have A, B, C matrices, and X, Y vectors. Technically speaking, a vector is just a special kind of matrix anyway. It's a matrix with just one column, but more than one row, you know? So like vectors are also matrices from a pure perspective. But these are properties of matrix multiplication. Another property of matrix multiplication, this one's kind of an important one, is if I take a matrix times the 0 vector, I get back the 0 vector again. Okay? So the matrix times the 0 vector will give me the 0 vector again. So this example 4, with that property in mind, starts to become obvious. Is there a solution? Is there no solution? Right? So in other words, this is really A times X equals to 0, right? But I'm telling you, if you have the 0 vector, right, and you multiply it matrix times the 0 vector, you get back the 0 vector again. So is 0 a solution to this? Well, yeah. Check. So we can take x vector, which is, of course, x, y, z, equal to the 0, 0, 0 vector, and this is a solution. Solves our system. So the 0, so what I'm trying to get you is to another theorem here. Follow-up theorem. I'll call this theorem 1. Theorem 2, Ax equals to 0 always has x equals to 0 as a solution. So a homogeneous system always has a solution. You just set all the variables equal to 0, it works, right? Now, is that the only solution for example 4? If you believe theorem 1, you should know the answer is no, because the determinant of the matrix of coefficients is 0, which means there have to be infinitely many solutions. How do we find them then? All right? That's where row reduction comes into play. Row reduction. So here's the deal. We take the matrix 1, minus 2, 3, 2, 4, 1, 4, 8, 2. We put some dotted lines right here, and we put 0, 0, 0. What I'm looking at here is A concatenated with B. So you take the matrix of coefficients and you glue the inhomogeneous term onto the last column. This is a way of writing the system of equations without writing the variables. It captures the structure of the system without actually the drag of writing x, y, z all over the place. But this has all the information of examples 4 system, right? It's the same thing. And then what you can do is you can do the things we did to solve example 1 for this system at the level of this notation. You can subtract equations, right? Like what we'll do here is we'll do row 2 minus 2 row 1, and I'll do row 3 minus 4 row 1. 1 minus 2, 3, 0. This line here is just decorative. It's to remind me that the 4th column has a different meaning. It's the inhomogeneous term. It's not part of the coefficient matrix. But formally, it's just a decoration. So if I subtract twice row 1, you see what I'm going to do? I'm going to clear out this 2 and this 4. That's why I did that. And then I have to think, okay, so I'm taking 4, and I'm subtracting 2 copies of minus 2 from it, right? So that's what? That's actually 4 plus 4. I get an 8 here. And then row 3 minus 4 times row 1. Well, minus 4 times row 1 is really going to give me an 8. So I get 16. There. Let's see here. Row 2 minus 2 times row 1. So I'm getting 1 minus 2 times 3, which is 1 minus 6, which is minus 5. Let's see here. Row 3, so minus 4, that's going to give me, minus 4 times 3 is minus 12. So 2 minus 12 is minus 10. All right, at this point, we've done what's called clear out under the first pivot position. The first pivot position, you just want to make your upper, like the highest thing to the left, you can make it. If you can get the upper corner and the matrix is non-zero, you start with that. If there's not something there already, you can switch rows and make something. As long as you've got something non-zero in the first column, you just flip the rows until you get it up to where you want. Another thing we can do is reorder the equations, right? Who says the first equation is the first, the second equation is second, third equation is third? You can relabel them, right? Which corresponds to flipping the rows. We can always flip rows in this algorithm I'm describing. What's next here? So our next pivot position is probably going to be this 8 here. I hate fractions, so what I do is I multiply this by, to make it match up, I'll multiply this by 8, I'll multiply this by 2, leave that alone. Now, this is not required. This is just me avoiding fractions, so, take it for what it's worth. you've probably started to notice that writing the fourth column of zeros isn't really necessary, right? It's going to stay 0, whatever you do. If you think about the operations I'm allowing, which is adding equations, multiplying an equation by a non-zero number is allowed, right? Think about that, right? So we can add equations, we can subtract them, we can add constant multiples. All right, now what I can do then to clear out above and below that, I can just take row 1 plus row 2, and I can take row 3 minus row 2. So this gives me 8 minus, oh, I'm sorry. What's row 1 plus row 2 is what, 0? We get what? Minus 4, 0, 16. I'm not doing anything to row 2. What happened? Row 3 minus, well, that's a 0, right? Yep.
The matrix, the one before you just did, why is the top right a 6?
Let's see. Oh, that's a good question, because I was supposedly multiplying by 3 by 8, wasn't I? What's 3 times 8? 24, yeah, that would be much better as 24, wouldn't it? Thank you. And then that makes this what? Not 4, but what? Sorry. Yeah, 14. Thank you. Very good. All right, at this point, we're almost done. Finishing blow, so to speak. Row 1 divided by 8, and row 2 divided by 2. So I get 1, 0, 14 over 8, 0, 0. Did I say 2? I meant 16. Sorry. Eventually I'll get with it. 1 minus 10 over 16, 0. All right, so this guys is what's called the RRF, reduced row echelon form of A with 0 slapped on the end of it. I mean, well, fine, I'll put a B back, but. So the point of doing these row reductions, this is what I'm showing you, is called Gaussian elimination, aka Gauss-Jordan elimination. Is that it takes the system and it reduces it to like a standard system. Now, if you look at the final answer, what does that actually tell us about the variables? It tells us something really, really pretty and simple. The solution, the equations that we have gotten to are x equals to, what is it, minus 14 over 8z, and y equal to 10 over 6z, right? AKA, what is that? That's, I can do better. Cancel the 2 out, right? Minus 14 over 8 is what? It's 7/4, yeah? So minus 7/4 z, and this is what, 5/3? Yeah, 5/3 z. Solution set. It is minus 7/4 z, that's my x. My y is 5/3 z. And my z, well, is z, such that z is a real number. So not only is the solution set infinite, Gauss-Jordan elimination gives me a way to find how to describe the infinite solution set in a nice orderly fashion. All right? Does this make sense? Now, I don't expect you guys to do row reduction on the test, the in-class part of the test, but I probably will give you some take-home, there'll probably be a take-home part of the next test where I want you to do row reduction on something more complicated. You'll need to find, you can use MATLAB or whatever to do that. I wanted to show you it by hand because I think it's important to understand what's going on with this tool that you're using. The reduced row echelon form of a matrix is a way of doing these row reductions. The computer does it for us, but this is what it is. I mean, let me show you guys one of the, well, here's a tool I like to use. If I can get the overhead thing working here. So if you go to my website, no internet connection. No internet connection. You best be kidding me. Yes, I'd like to connect. Do I think Liberty's network is secure? I have my doubts, but I still want to connect. It's just a chance I'm willing to take. All right, there we go. It's working. Hooray! Now, if you go down here eventually, my old schedule, with room numbers that no longer exist. Fun fact. Let's see here. Links to websites that do the math for you. I'm fond of. I mean, Wolfram Alpha will do it. Yeah, sure, great. But this is actually. You guys will take probably Math 221 if you haven't already. You will soon, or possibly 321. And there you will need to learn how to do row reduction. So you don't have to do it right now, but it is fun to notice that, like, I can check the work we just did. Can you guys tell me what the matrix is? I can't read it from here. For example, 4. What was the numbers?
1, -2, 3.
Okay. Then,
4.
Oops. 4, 1. And then 4, 8, 2. You guys know how I make my example now. I told you my secret. It's here. And this website's pretty awesome because it actually shows you the, well, at least, I mean, there's many different ways to get to the end point. Like the reduced row echelon form is unique. The algorithm to get there, there's lots of different ways you could do it. All right. So this is just one way, but we should agree on the answer. Yeah. As you can see, 1, 0, 7/4, 0, 0, 1, minus 5/8, 0. I think that's what I have. Yeah. Oh, no. I probably just copied it down wrong, though. Oh, yeah, look. See what happened? My vision for the lose. I somehow managed to see this as a 6 when I looked at it from over here. This is sad, but true. That became a 6 to me in my vision. Sadness. This was a 16, right? Which is actually going to give us 5/8. So this equation would be x plus 7/4 z equals to 0. This equation is y minus 5/8 z equals to 0. So what it says is you can write x and y in terms of the z variable. We can use the z variable as a parameter for the solution set, right? Okay, so anyway, this is really nice because, you know, if you wanted to do something like, I mean, you could make this 3 or something, and then check it out. Here's the solution. If it exists. Does it exist? It exists. Woohoo! X equals to minus 15/2. Y equals to 11/4, and z equals to 5. And there's the row operations and the Gaussian elimination that you needed to do to get to it. Right. Now, you guys can use MATLAB, Mathematica, Wolfram Alpha, whatever. It's fine. All right. So enough about that. That's what we need to know from linear systems, actually. We also need to know how to multiply matrices. So let me get to that now. There are websites for multiplying matrices, but I don't really have a favorite one. They're all kind of a little bit, well, I want to say hokey, but for some reason hokey is not an insult in this state. Everywhere else, let's see here. All right, so that's my quick introduction for you guys into systems of linear equations. I think it's important because otherwise you don't really fully understand what we're doing, perhaps the end of today and especially tomorrow. So just a little bit on matrix math. A plus B, C times A, you know, etc. Unsurprising, all right? For example, if I take the matrix And I can take matrices of functions just the same, like cosine of t, t squared, 1, e to the t, right? And if I multiply this by 3, what do you think that means? Oh, heck, let's multiply by 3t. What that means is you multiply everything, each component, by the same thing. So it works just like multiplying vectors times numbers, right? You multiply the number times every component in the vector. So the definition is just this CA, the ijth component of that, is equal to C times Aij, which says we multiply component-wise. Addition, much the same. If I have e to the t, 1, 0, e to the, I don't know, let's say cosine t, right? And I add it to e to the minus t, 3, 0, sine t, what do I get? I'll put some dividers in. 0 plus 0 is 0. Cosine t plus sine t. So there you go. I mean, you can add matrices of functions. You just add each matching component. So like the definition for matrix addition is also very unsurprising. A plus B is a new matrix, supposing A and B have the same size, and the new matrix we just get from from adding matching components. You can also do things like differentiate or integrate matrices of functions. How would you do it? What do you think dA and dt, what's the ijth component of that going to be? Let me be more specific. What if I said differentiate, this matrix here? What would you get? I think you guys know. d dt. Take the derivative of this matrix, we get 3, 6t squared, 3, and then product rule, right? So 3 times 1 plus t e to the t, yeah. So the definition, if you want me to be honest, is simply this. It's just differentiate component-wise. So I just differentiate the ijth component with respect to time, and I do that for each component. All right? This is how we define matrix, differentiation of a matrix. Just like we do differentiation of a vector, component by component. Same for integration. Here's some fun, I guess the other thing, though, that I haven't talked to you about yet is matrix multiplication, which is admittedly a little bit, we did a little bit of that already. I have introduced, I just erased it, but I multiplied what? I multiplied a m by n coefficient matrix by a n by 1. So this was A, this was X, and we got B, right? So this was m rows, n columns. This was 1 column, n rows. And how big was B? How many components were there in that B? There were many components as there were equations, right? There were m of them. So this is actually a m by 1 matrix. So here's the definition more generally. If we have A is m by, let's say, p, and B is, let's say, p by n, then AB is m by n, where AB, the ijth component in it, is equal to, let me think about this, it is equal to the dot product of the ith row of A dot product with the jth column of B. So that's how we multiply matrices. We take dot products of rows of the left thing with columns of the right thing. That dot product will make sense provided that the size of the rows of A matches the size of the columns of B, right? For this dot product to be meaningful, these both have to be the same size vectors, right? An example. What example am I on? Looks like 5, huh? I guess it's 6 if I call this. Let me be honest. This was example 5. This was example 6, actually. So example 7. I don't feel like I've done my job in a given day if I don't get at least to example 10, right? You're owed at least that much, I think, in a given day. Yowzers. All right. Okay, so here's one. We could do 1, 2, 3, 4 times, let's say here, 0, 1, 2, 3. So we do some color coding here. We take the dot product of this one with that one. What happens when you take the dot product of 1, 2 with 0, 2? What do you get? 4, right? Then we take the dot product of 1, 3 with 1, 2, right? So 1 times 1 gives me 1. 2 times 3 gives me 6. 1 plus 6 is 7. Let's see here. And then to get the next one, I should take to get the 2, 1 position, so to speak. If I can find a blue marker, I feel better about my life. Blue marker, show yourself. Aha. All right, so we take this guy, dot product with that, to get this one here. So I do 0 times 3, which is 0, plus 4 times 2, which is 8. And let's see here. How about this one? That gives me 3 plus 12, which is 15. Now, by the way, guys, this is something I might test in the in-class part of the test. So if you're not already up on multiplying matrices, I would like you to learn how. It's an important skill to have going forward. There's no time like now to learn. It's a relatively small part of what we're doing, but it's an important calculational step, certain places here and there. So I do need you to know it. Just say it. Now, if this is A and this is B, then we can also calculate B times A. What do we get if we calculate B times A? All right, so this dotted with that gives me 1 plus 3. I get a 3. Next I get, tell you what, let me write down the one step, and then I'll write down one step here. It's not too much for me to write. 1 times 3. Let's see here, I got 2 times 1 plus 3 times 3. I've got 0 times 2 plus 1 times 4. 2 times 2 plus 3 times 4. I don't typically write down that step. I usually just do it in my head, but you know, since we're starting here, 3, 2 plus 9 is 11. That looks like a 4. 4 plus 12 is 16, right? As you can see, that's not equal to AB, right? In fact, not even one component matches. They're pretty far from equals, right? So this is one of the important features of matrix multiplication is it's not generally commutative. It's not usually going to be the case that A times B is equal to B times A. All right. All right, so they're generally pretty much unrelated. I mean, there's going to be some relation. I mean, it's not, they are both built from A and B.
Yeah.
So you can say things about like the rank of the matrix. There are things in linear algebra you could say, but in terms of just generic pattern matching, not really. In fact, what AB is based on A and B is rather, you know, it's pretty non-obvious, I think. I mean, there are some things we can say. Here's one of the main theorems of matrix multiplication, which is super useful. If you have A times like B1, B2, B sub, let's say, sub n. So in other words, I've got a matrix times a bunch of column vectors stacked together. Then there's a column by column proposition. In other words, I can do this as actually A times B1, A times B2, A times Bn. So like when you multiply a matrix times another matrix, you can think about it by multiplying one column at a time and stacking them together. For example, if you use this backwards, I can see from this that 1, 2, 3, 4 times the vector 0, 2 is going to be equal to 4, 8. So what I'm doing is I'm looking at this piece coming from that piece. So like this times that has to be that. So you can rip it apart in this way. That is actually very useful and important to us. Okay. So I think that's almost everything I should say. Just a little bit of calculus. Here's the main thing. If I have the derivative with respect to time of two matrices, and you can multiply those matrices, then guess what? There's a product rule, and the product rule is just what you want. It's dA dt times b plus a times db dt. This is nice. There's also a product rule for like scalar multiplication. So if I have d dt of a scalar function times a, then guess what? It's df dt times a plus f times dA dt. The last thing is also true for a vector. So like particular, special case. If we have derivative with respect to time of, say, a function times a constant vector v. So here's a function. Constant vector would have dv dt equals to 0, all right? So suppose you have a constant vector times a function of time. It's very simple. You just differentiate the function and you multiply by the vector. That special case is actually the one that's most important to us in our upcoming work on what are called eigenvectors. All right? All right, I think I've said enough now that we can actually start working on systems of differential equations, and hopefully it won't be too much of a shock to your system because we've already looked at matrices and systems at least a little bit. So I'll do that after a short recess. You want to hit stop there?